Welcome to this Engineering Explainer. Today we're going to completely unpack the complex math behind automotive network load. Look, if you've ever struggled with calculating exactly how much bandwidth a controller area network, a CAN bus, is actually using in a real-world system, well, you're absolutely in the right place. By the end of this walkthrough, you're going to have mastered the exact mathematical intuition you need to calculate true network load, and we're going to account for every single hidden bit. So let's dive right into it.
So the absolutely crucial question we have to ask ourselves is, how do we guarantee this network doesn't just crash from traffic overload? How do we prevent catastrophic data collisions? Well, the answer lies in mastering the mathematical formulas that dictate exactly how long a data frame physically becomes once it hits the wire. Today, I promise you'll learn exactly how to derive those exact percentages so you can guarantee your network stability out in the real world.
Okay, here's our roadmap for mastering this. First, the automotive data hook. Second, anatomy and stuff bits. Third, the math breakdown. Fourth, a real-world walkthrough. Fifth, the gotchas. And finally, a recap and takeaways.
Section 1. The automotive data hook. Let's go from macro to micro.
To really understand how a network overload happens, we need to zoom all the way in and dive straight inside the data material itself. Because the payload, the actual useful data you're trying to send, is really only a fraction of what travels across the bus. The rest of it is hidden overhead. So let's introduce a concept called the stuff bit. To really grasp this, I want you to picture a marching band. Imagine them trying to stay perfectly in step without a conductor. Eventually, they're going to drift apart, right? Well, in a CAN network, if a receiving node gets a long, uninterrupted string of identical bits, like a long line of zeros, its internal clock actually drifts out of sync with the sender. To prevent this, the protocol automatically injects a forced bit of the opposite value. That is your stuff bit. It acts exactly like a drummer hitting a cymbal, forcing a state change so all those receiving nodes can snap their internal clocks right back on beat.
Section 2. Anatomy and stuff bits. Where exactly do they live? So if the protocol is constantly injecting these extra drum beats into our data stream, we have to know exactly where they are legally allowed to pop up within a single frame, because every single stuff bit adds physical length to the message, which eats up precious time on the wire. Let's look at the physical anatomy. I want you to picture highlighting the frame in two very distinct colors. First, color the zone from the start of frame bit all the way through the identifier, the payload, and right up to the end of the cyclic redundancy check, the CRC, in green. This is our active stuff bit zone. Right here is where the protocol will actively insert those drummer beats. Next, color the zone from the CRC delimiter to the inner frame space in red. This is the forbidden zone. For these final 13 bits of the frame, no stuff bits are ever inserted, no matter how many identical bits happen to occur.
Section 3, the math breakdown. It's time to derive the rules.
Now, because the number of stuff bits depends entirely on the random arrangement of ones and zeros in the payload, we can never know exactly how long an arbitrary frame is going to be ahead of time. So we have to systematically derive the absolute worst-case scenario. Check out equation 4.1 from our source text. This is the atomic breakdown of a CAN frame. The total frame length equals the start of frame plus the identifier, plus the control field, the payload data, the CRC checksum, the CRC delimiter, the acknowledgments, the end of frame, the inner frame space, and finally, our stuff bits. Every single one of these physical fields adds literal microseconds of overhead that just bloats the actual data payload. But wait, how do we mathematically solve for a variable like stuff bits if it's constantly changing?
Well, we solve it by calculating the absolute mathematical maximum. Take a look at equation 4.2. The maximum stuff bits, SB as a function of n, equals the floor of n-1 all divided by 4. Let me define these variables for you. N is the total number of bits in our green zone. Remember, the parts of the frame that are actually subject to stuffing. The hard rule is that after every 5 identical bits, at most, one stuff bit is forced into the stream. And those floor brackets, that means we must always round down to the nearest whole integer, because obviously you cannot have a fraction of a bit on the wire. Okay, so when we take equation 4.1, substitute in the maximum possible stuff bits from equation 4.2, and then combine all the static fields for a standard 11-bit identifier frame, we arrive at this brilliantly elegant derivation, equation 4.3. The maximum frame length simply equals 55 constant bits of overhead, plus 10 bits per byte, multiplied by s. The variable s is just the number of payload bytes you're sending. Think of that 55 as your absolute non-negotiable tax just for using the network. And the 10 times S part, that's the padded size of your actual useful cargo.
Section 4, Real-World Walkthrough. Let's apply the math.
Let's move from theory right into practice and tackle a practical engineering problem based strictly on Beispiel 1, from the source equations. We'll methodically set up our known variables. Let's say we have a CAN cluster running at a bit rate of 500 kilobits per second. Our system requires us to send 1,200 frames every single second, and each of those frames carries a maximum payload of 8 bytes. Our job, we need to find the worst-case bus load.
All right, step 1. Let's find our maximum frame length using that elegant equation 4.3. We take our 55 base overhead bits and we add 10 times our 8 bytes of payload. Well, 10 times 8 is 80. Add the 55 and boom, we have exactly 135 bits per frame. Step 2, let's apply equation 4.5 to actually find the load. Bus load equals the frame length multiplied by the number of frames per second, all divided by the total bit rate. So we take our 135 bits per frame and multiply it by 1,200 frames per second. That gives us 162,000 bits being shoved onto the wire every single second. Now we just divide that by our network's absolute physical speed limit, which is 500,000 bits per second.
The result is 0.324. Move the decimal 2 places over, and we have mathematically proven a maximum bus load of 32.4%. This perfectly and elegantly demonstrates the unbreakable relationship between your frame size, your transmission frequency, and your hardware's bit rate. You now possess the mathematical intuition to prove exactly how much bandwidth is being consumed.
Section 5. The gotchas. Let's talk common pitfalls.
Now, engineering is never quite that simple, is it? Let's shift focus for a second to the tricky edge cases that routinely trip up engineers during design reviews. The absolute most common pitfall is forgetting which protocol standard you're actually using. Everything we literally just calculated was for an 11-bit standard identifier. But what if your system architecture suddenly dictates a 29-bit extended identifier? Well, you cannot use that 55-bit constant anymore, because the extended ID adds far more bits to the header, which dramatically expands our green stuff bit zone.
As derived in section 8.6 of the text, look at equation 8.8. For a 29-bit extended identifier, your base overhead constant jumps from 55 all the way up to 80 bits, so the formula becomes 80 plus 10 times your payload bytes. If you accidentally apply that standard 55-bit constant to an extended ID network, your entire bus load calculation is going to be dangerously wrong, and you could potentially hide a fatal network overload.
And here is the ultimate mathematical sign error pitfall. The floor operator in our stuff bit calculation, equation 4.2. The source text explicitly notes that those brackets indicate rounding down to the next smallest integer. You must always round down. If the math spits out 4.75 stuff bits, you do not round up to 5. You only get 4, period. Accidentally rounding up will artificially inflate your frame length calculations, and you'll end up failing your design review for completely the wrong reasons.
Section 6. Recap and takeaways. This is your survival guide.
Let's lock these core mathematical concepts firmly into your long-term memory. Think of this as your survival guide for automotive network calculations. Number 1, never forget the drummer. Stuff bits are protocol-inserted synchronization drum beats meant to keep receiving nodes from losing their internal clock timing during long strings of identical bits. Number 2, for worst-case mathematical derivations, standard 11-bit IDs carry 55 bits of base overhead, while 29-bit extended IDs carry 80 bits of base overhead. Number 3, when you're manually calculating max stuff bits using the n-1/4 formula, always strictly apply the floor function and round down to the nearest integer.
So I want to leave you with this final, provocative thought. Armed with these exact derivations and the intuition behind how they work, can you absolutely guarantee your next embedded network design is truly overload-proof? Well, you now have the exact math to back it up. If you found this breakdown valuable and you want to master the real-world math behind complex systems, hit subscribe for more EMC and automotive communication protocol survival guides. Until next time, keep calculating the worst case so you can build for the best.